Hello everyone and welcome to my presentation. My name is Chouaib. I'm from Algeria. I'm PhD student at Zughras University. The main focus of this presentation is about the effect of induction heating stress remedies on piping reliability. In this slide we will go through an introduction, then we will discuss the intergranular stress corrosion cracking model. After that we will talk about welding residual stress mitigation, then we will discuss the obtained results, and finally a conclusion. To address the effect of intergranular stress corrosion cracking on the probability of leak in boiling water reactor piping, we have introduced some changes to the model of intergranular stress corrosion cracking for the probabilistic fracture mechanics press code. This semi-empirical model is based on experimental and field data compiled from several sources. Using probabilistic techniques, the model addresses various stress corrosion phenomena, including crack growth, crack initiation, and linking of multiple cracks. The model also considers the effect of residual stresses in addition to cyclic stresses resulting from normal plant operation. Residual stresses, which are an inherent result of conventional welding processes, have long been known to play an important role in the failure of structural component. Such stresses can have a beneficial or detrimental influence depending primarily on whether they are tensile or compressive at the inside surface of the pipe. Residual stresses undoubtedly are influential in both the initiation and propagation of cracks. The purpose of this paper is to review the influence of residual stresses on the reliability of piping under intergranular stress corrosion cracking. A procedure such as induction heating stress improvement is a means of altering the residual stress pattern in a pipe. Examples of the use of these techniques to the initiation and the growth of stress corrosion cracks in pipes are presented for various pipe size and residual stress distribution. The effectiveness of induction heating stress improvement as an internal countermeasure for intergranular stress corrosion cracking depends upon the level of service stress as well as the crack size, and its large benefits is immediately apparent. The piping reliability model was developed based on the probabilistic fracture mechanics concepts. The computational procedure for the estimation of leak probability combined various random variables, such as initial crack size distribution, flow or crack detection probability, crack growth relation, and the deterministic stress history. The probability of leak at the pipe location analyzed is equal to the probability of a crack growing to the corresponding critical size within the specified time using Monte Carlo simulation. The methodology recommended in praise for modeling intergranular stress corrosion cracking in stainless steel pipe is presented, and all cracks are two-dimensional semi-elliptical anterior surface cracks, generally circumferentially oriented as shown in this figure. Praise separate the overall time to pipe leaks into 3 steps: time to initiate a very small crack, time spent growing small cracks at initiation for velocity mu1, time spent growing larger crack at fracture mechanics velocity mu2 to become through wall cracks. The growth of very small cracks that have just initiated cannot be treated from a fracture mechanics standpoint. Some researchers concluded that equations used in praise to calculate the stress intensity factors in order to simulate crack propagation and modification. In our modified praise, this modification has been accomplished using well-accepted expression given the ASM handbook. Residual stress play a very important role in the initiation and growth of stress corrosion cracks, hence they are important in the analysis of the reliability of sensitized welds in boiling water reactor piping, and praise included extensive provision for their consideration. Several techniques for controlling or altering residual stresses on the inside surface of gas welded pipes are presently being investigated within the pressure vessel and piping industry. These include induction heating for stress improvement, last pass heat sink welding, and backlay welding. These techniques are based on the principle that the residual stresses are influenced by the thermal history of the pipe. Induction heating stress improvement is a means of altering the residual stress pattern in a pipe. This is accomplished by passing water through the pipe while heating it from the outside with an induction coil, as shown in this image. It appears that the post-induction heating stress improvement residual stress can be adequately described as axisymmetric with a linear through-the-wall gradient for a given pipe size and thickness. Such a spatial distribution can be characterized by a single number, such as the value of the stress at the inner diameter. This image shows stress distribution, deformation, and temperature distribution during heating and after cooling. In this study, a finite element residual stress analysis of IASI 304 and stainless steel pipe, interior diameter of 300 mm, while thickness of 30 mm, was conducted for girth welding and welding plus induction heating stress improvement treatment using ANSYS 20R2. To induce the induction heating stress improvement treatment, the Ansoft Maxwell program simulation tools are linked within the ANSYS workbench interface by definition of the project schematic as shown in this figure. Here we have two study cases of axial and hope residual stress distribution versus the wall thickness after induction heating stress improvement. The first for young cracked and the second one for complete circumferential cracked pipe with depth of 3 mm. Note that induction heating stress improvement treatment after welding can convert the tensile weld residual stresses to compressive values. Thus, the computational modeling studies have demonstrated 1. The feasibility of predicting the effects of the induction heating stress improvement process on weld-induced residual stresses, and 2. The applicability of computational model as a tool for better understanding the consequence of not meeting recommended guideline for induction heating stress improvement parameters in these cases. If a change in residual stress is desired in midlife, it can only be changed to axisymmetric self-equilibrating throughout the wall. This figure presents results for the cases where residual stresses were changed by induction heating stress improvement treatment at 20 years. The following conclusions are obtained from the numerical and analytical results. The residual stress after induction heating stress improvement can be in comparison at the crack type, which mitigates sensitivity to intergranular stress corrosion cracking. There is a large margin for the initiation of cracking from a pre-existing flow during induction heating stress improvement, so long as the crack depth is not greater than 45% of the thickness. A simplified procedure to predict induction heating stress improvement effectiveness for the pre-flowed pipe was proposed, making use of the calculation of the stress intensity factors by the superposition principle. The effectiveness of induction heating stress improvement as a permanent countermeasure for intergranular stress corrosion cracking depends upon the level of service stress in the operating condition as well as the crack depth and its configuration. A long circumferential crack will be prevented from further extension by induction heating stress improvement if the depth is under 30% of the thickness and the service stress is under 0.75 of membrane stress, which seems to be likely in normal circumstances. If a change in residual stress is desired in midlife, it can only be changed to axisymmetric self-equilibrating through the wall using Empress code. And thank you for your attention.